All right, let's first look at the example. This is the same homogeneous equation we've been looking at, or operator we've been looking at. So we're just changing the right-hand side, x squared. For example, here cosine 2x. All right. So the guessing is that, of course, if you try x squared cosine 2x, you will have x squared cosine 2x back, and this will change a little bit, additional terms to kick in. So let's see what happened if we try this function. So L is again representing the operator associated with the left-hand side of this equation. So we're trying this one here. Oh, I love cosine 2x. So I'll skip this detailed calculation. So you have to plug it in here and do all this at second derivative and collect, maybe we're going to collect cosine 2x and sine 2x, you surely kick in. So after you differentiate it 2 times, and if you collect in terms of cosine 2x and sine 2x, and this is what we get. So because of this x squared part, it got fairly complicated. But the goal is that we definitely want to try x squared sine 2x so that we have a probably similar form, which is understandable because of this constant, coefficients are constant. It's easy to see that we're going to have a similar form like this. From there, we hope that we can eliminate this sine 2x when we want to have this x squared and cosine 2x back. So we want to keep this 3x squared cosine 2x. So by considering other examples, we want to cancel these constant and degree 1 multiplied to cosine x and entire the sine 2x. So let's see what we get when we try L times L of x squared sine 2x when we go through this. So after you go through and you simplify, these are the coefficient of cosine 2x and 8x minus 2x squared and 2 minus 2x minus 3x squared. It's supposed to be similar to each other because it only differ by just slightly different order of repeating sine and cosine. Okay, so the first goal is that how we're going to combine these two to get rid of the sine 2x. You can see you can't do that entirely. We can knock down only this x squared part by multiplying 3 here and 2 there, and that's going to cancel the sine 2x part. So that's the sum calculation you have to go through, and you can see the coefficient gets messy. So what is clear to us at this stage by looking at 2 things is that we can get rid of this x squared sine 2x term. And then we have to get rid of x times the sine 2x part and constant times sine 2x. When we have these 2 conditions, just to play with constant multiples of these 2 expressions, you can get rid of only 1 terms at a time. So you have to look at different things. How can we get x times the sine x, a sine 2x, or just the sine 2x, so that we can get rid of all that. And then we have to think about how to get rid of x times the cosine 2x and s times constant times cosine 2x. A lot of things to get rid of. So just looking at this one and come up with a coefficient to do all that will be very, very inefficient. Maybe we can manage to do that, but it is certainly not something that seemed like an efficient way to do it. What we have to focus on is that what happens when you stick in x squared times this sine and cosine is this is what we get. And to get rid of, here you just using this when we can get rid of x squared part, we still need to get rid of this x parts and constant part. And what are we going to try? We need more information or more identities like that so we can cancel more terms. Definitely we have to play with x times cosine 2x and x times sine 2x, and from that you can see we will have those terms back and we can play with those. So I think next thing we should try is this x times sine 2x. Let me do the cosine 2x first. So it's a cosine 2x and L of x times sine 2x. And that will give you these type of a coefficient, linear, not quadratic. And from there we may be able to get rid of x times sine 2x. We'll have x times sine 2x and x times cosine 2x, and these are the terms we will get, and we can play with a linear combination of these two things to get rid of what's unnecessary part, unwanted terms that are shown up in our first one. And of course we can play cosine 2x and L of sine 2x. And for those, after you go through this operator, you will only have sine 2x and cosine 2x as the main terms. So we can play with that to get rid of the rest of the part. We definitely don't want to look at the 6 complicated expressions and think about how to juggle to get rid of all that, and that part is no longer fun. So the best way to do here is that this is going to be a linear combination of all 3 types. So you have to just go and write down the general shape of a linear combination of all these 6 functions inside this L operator and simplify as much as you can in here. And then we have to compare the coefficients. Now, let's write down all the possibility here. What we are looking at here is first, think about a1, x squared cosine 2x. The linear combination we get out of this is just multiplying a constant. So that's what you can get, and they can pass inside this operator. And of course we have to do it with the sine 2x, but let me just look at this cosine 2x parts, and that's kind of reasonable thing. So here's linear combination of that one will give us b1 to x cosine 2x. And if you could look at this part, it's a c1 and cosine 2x. So all possible linear combination of this 6th term can be represented, and part of it, half of it, can be represented in this way. And then we continue in the other line. Here's a2 x squared. I'm collecting the sine 2x part. Here's a sine 2x, and plus b2, and this part here, x times the sine 2x. And the last part is a c2 sine 2x. So all the linear combination can be simply represented by this general form, and you have to put this one into this operator and write it as simple form as possible. But also, because all this cosine 2x are common, you can represent it in the following way. a1, if you factor out those cosine 2x, a1 x squared, b1x plus c1 cosine 2x, that's this part, and a2 x squared, b2 x in here, that's the second term, and c2 after you factor out all the sine 2x. So by looking at what happens in this first 2 example and thinking about what's going to happen if you tried lower degree of this monomial multiplied to these trigonometric functions, then we arrived at this is something we should ultimately try. So however, when you look at the problem like this, polynomial monomial multiplied to the cosine 2x, and this is ultimately what you have to try. Just looking at some samples is not going to give you a quick answer. Okay, now this is massive expression, but that product rule of the second derivative will be very, very useful. So let us remind that rule. Well, let's first the operator, y double prime minus y prime plus y. This is what we're doing to each of the functions. So remember that part. So the second derivative of this whole thing is what we're going to do. This is a product of one term, the product of 2 functions, and another term, product of 2 functions. So we'll apply that product rule of a second derivative 2 times in each of the parts, since they're linear combination like this. So this part will go like this, differentiating this one 2 times. So that and that will disappear. We only have 2a1 cosine 2x. And 2 times differentiating this one times that. So if you differentiate that, 1 time is a 2a1x plus b1. If you differentiate that 1 time, it's a negative 2 sine 2x plus, and differentiating this one 2 times, so that would be a negative 4 out there, and with that entire quadratic, so let me write down in the second line. And here, if you differentiate that 2 times, we have negative 4 out, so let me write down it's negative 4 here, and entire polynomial is still there, like this. But the other part, after you differentiate 2 times, you're back to cosine 2x. So that would be the derivative, second derivative of that part. If you did the same thing, it's quite similar. So I'll just repeat this much with the sine and cosine pretty much swapped around. So what we get is the derivative of this one 2 times. So it's a 2a2 sine 2x. 2 times the first derivative times the first derivative. So derivative of this one time will be 2a2x plus b2. Differentiating this one time is a 2 times cosine 2x. This one not differentiated here. This one differentiated 2 times will give you negative 4 out there and back to sine 2x. So this entire part corresponds to the second derivative of this entire thing. Everything is in terms of cosine 2x and x times cosine 2x and x times sine 2x and so on. So let's move on to the next part, which is negative of the first derivative. So I'm going to put giant parenthesis here, negative. So if you differentiate this one time, you will have differentiating this one is a 2a1x plus b1 and cosine 2x not differentiated. And if it is differentiated, you're going to have a negative 2 out there, and this one not differentiated. Right, it's written there. So that's back to sine 2x. So that's the derivative of this part. Let's do the same thing, and which I will skip. All right, so I did it here. We're differentiating this one time, the product rule, product of two functions. So that's the derivative of this factor, 2a2x b2, sine 2x not differentiated. I kept this first factor and differentiate sine 2x. That becomes cosine 2x and 2 out there. So that's going to be the entire result of the y prime with negative outside. Y is just repeated here. The whole thing, the entire y will be repeated. Y exactly. So it's written there, so I didn't write it down. So you have to collect all those things. It's a lot of work. It's really collect all this thing and see what happens. So when we collect it all together and everything that has a cosine 2x, and inside and here collected it as a polynomial with all the constants in front of x to the first and x squared, and similarly in the sine 2x. So this mass expression came out when we went through that second order linear operator. Let me remind you what our phi x was. Our phi x was actually simple. What is in the right hand side was x squared times the cosine 2x, and this is what we wanted to get. So this is what comes out if you try that general solution with a1 and a2 and a3, a1 and a2 and b1 and b2 and c1 and c2 in front of all that x and x squared multiplied by cosine 2x and sine 2x. So what we want here is we want this entire thing to be 0. So let's see there 6 coefficient that exactly matches the number of unknowns we have, unknown coefficients, a1, b1, c1, a2, b2, c2. There are 6 of them, and you can see there are 6 coefficients to match in here. This part did not appear in here. Only this x squared times the cosine 2x appeared. So that was this one. We want things to be 0 as well. And of course, we want this entire part exactly 1. So that we want this thing to survive. And this part is all 0. This is what we want. This disappears, and this part disappears, like that. So if there's A1, these 6 coefficients to satisfy the 6th condition, with this part being exactly 1 like that, and that will be a particular solution to that non-homogeneous problem. So here's the summary again. Let me scroll down a little bit. We wanted to solve this non-homogeneous equation, and by trying some of our guessing, we realized that we should really try this type of example, cosine 2x, with all the lower degree term, polynomial term. We should also try sine 2x with this lower degree polynomial terms like that. So when we went through this operator, it is organized in this way, and every coefficient must be 0 except that coefficient of x squared in there. And we have to solve the system of 6 equations and 6 variables. This is even by hand, it takes a long time, but when you do that, we have the following solutions. So this turns out to be the answer. It's a particular solution. So you may guess that I probably did not calculate this by hand. I use computer software actually to solve this system of 6 equations. But this is the only 6 numbers that satisfy these linear equations here. So this is a particular solution.